Hello, this is Dr. Armand again, bringing you another exciting lecture in General Chemistry 1 laboratories. Today, in this lecture, we'll be discussing Lab 4, chemical reactions, chemical reaction types, and their equations. So we'll be investigating things, for example, what are signs of a chemical reaction has occurred, balancing chemical equations, and discussing the different types of chemical reactions. So sit back, relax, and enjoy the show. So this is the fourth lab in this General Chemistry 1 lab series. And so first we want to just discuss briefly what are signs to indicate a chemical reaction has occurred. And there are things you can observe that would indicate that a chemical reaction has occurred. So one is a visible color change. So for example, if your solution is colorless and then you add another uh, solution that is colorless and you form a solution with a different color, or you form a solid, that would be something like a visible color change. So if you have two solutions that you mix and you see a solid form from that, that's a sign that a chemical reaction has occurred. Or if you have, say, colorless solutions, you mix them, you see a change in the color of solution. So that's something to indicate that a chemical reaction has occurred. The next one is the evolution of a gas. So there are certain anions, for example, that when you react with an acid or a base, they form distinct gases. And so, for example, here we have three ions: carbonate, ammonium, and sulfite. And so when you react these ions with, in the case of carbonate and sulfite with a strong acid, you produce a gas, or any acid. It doesn't have to be a strong acid. It works more readily with a strong acid. And then when you react ammonium with a strong base, it produces a distinct uh, gas. And so with carbonate, when you react carbonate with an acid, and this could be something like, HCl, HI, etc. Any acid, and a good indication you have an acid is most of the time hydrogen is going to be the first element in the chemical formula. That's how you know something is an acid, and it works like 99% of the time. So when you react a carbonate with an acid, you produce CO2. And so that's one of the things that's concerning scientists as the ocean acidifies, is when the ocean acidifies, it reacts with the coral reef, which is carbonate, to produce CO2. So carbonate is an ion that if you react with an acid, you'll produce CO2. Also, in San Antonio, there's hard water. Sometimes you collect hard water deposits on your shower head. If you take the shower head and kind of soak it in vinegar, over time it will, you could say, react with all the carbonate to remove the hard water deposits from your shower head, clearing up the shower head. Again, because carbonates react with an acid to form CO2. And so vinegar, which is a weak acid, will do the job just fine. Next, we have sulfites. So sulfites, when we react with an acid, again, we're looking at things like HCl, HI, etc. This produces sulfur dioxide, SO2. And so that would indicate the presence of sulfite in solution if it produces SO2. So again, carbonate and sulfite react with acids to form gas. Now ammonium, and notice that carbonate and sulfite are anions, they react with an acid to produce a gas. Whereas ammonium Ammonium is a cation. It reacts with a strong base. So for example, or any base, sodium hydroxide, potassium hydroxide, etc. And so a strong base, as you probably learned in the lecture, is something that contains a hydroxide, usually group 1 or heavier group 2 hydroxides are strong bases. And so when you react ammonium with a base, you produce ammonia, which has a very distinct odor associated with it. So these are some ions that react with either an acid or a base to form a gas. Now the next series of evolution of gas we're going to talk about involves what was referred to as the splint test. So the splint test is where you take a match. We can have a little flame on it or an ember on it, and you put it in the presence of certain types of gases, it will behave differently. And so here, if we have hydrogen gas, so the splint tests positive for hydrogen gas when you hear a popping sound. So if you move the splint near your test tube where the gas is being produced, and you hear a popping sound, that would indicate the presence of H2. So to give you a quick example, if we take, for example, we react magnesium solid with HCl, we produce a magnesium chloride and H2. So if you were doing this experiment in a test tube, it would produce hydrogen gas. You would take your splint, which is like a match, put it near the mouth of the test tube and listen for a popping sound. And if you should hear a popping sound when you react magnesium with HCl because H2 is being produced. So this would confirm the presence of H2 as a product. And this is with the splint tests. Now with oxygen, and the reason H2 makes a popping sound is because when you bring the splint or the match near the mouth of the test tube, it ignites the H2, and then the H2 combusts with the oxygen in the air to produce a popping sound. So when you combust the hydrogen, a popping sound results, and that's why the popping sound occurs, because H2 is combusting with the oxygen in the air. Now with the splint test positive for O2, this is test positive when the match or splint flares back up, reflares or flares back up. So you could say the flame is brighter. So as you bring the flame near the mouth of a test tube where oxygen is being produced, since oxygen is the fuel for combustion, when you add more oxygen, the flame gets bigger, brighter, flares back up. Just like if you ever gone and done had a cookout where you're using charcoal, you know, to get the flames bigger on the charcoal, what you do is you fan it real fast to provide oxygen. The oxygen causes the flames to get brighter. Same thing here, as oxygen is being produced, you bring the flame next to it, it becomes brighter. Now for CO2, here CO2, if CO2 is present, it's going to extinguish the flame or splint. And this is because CO2 does not support combustion. That's often what's found in fire extinguishers, is CO2 gas, or a form of CO2, because it doesn't support combustion, it puts out the flame. So this is how the splint test can be identify hydrogen, oxygen, and carbon dioxide gases. So you can have evolution of a gas. Another type of sign a chemical reaction has occurred is the evolution or absorption of heat. And we refer to these as exothermic or endothermic reactions. So exothermic means it evolves heat or releases heat. Endothermic means it absorbs heat. And so a very classic example of an exothermic reaction are combustion reactions. And we'll talk more about combustion reactions in just a moment. So all combustion reactions are exothermic. So for example, when you go have a cookout and you're using a propane grill, propane is being combusted with the oxygen in the air to produce heat, which cooks your food. And so that's a very common reaction that is exothermic. Now, to give you an example of an endothermic reaction, for example, you have a muscle sore or something that requires you to use an ice pack. Usually you shake it or you kind of twist it, and it produces an endothermic reaction which absorbs the heat from the surroundings, giving that cool feeling to the ice pack, for example. And then lastly, a good sign that a reaction has occurred is the formation of an insoluble solid. So here you start with two solutions, you mix them, you form at least one solid. So these are all signs that a reaction has occurred. So now we're going to talk about chemical equations, which are like the recipes for chemical reactions. Just like you have a recipe to make cookies, there's also a recipe for chemical reactions. And so as you probably learned in the lecture, if you're taking it, the left side of the recipe is our reactants, the right side are products. And so reactants are what you start with, products are what you end up with. And one thing you have to remember is that in chemical reaction, you can't destroy or create atoms. All atoms have to be accounted for. So however many atoms of carbon you have on the reactant side, you have to have that many carbon atoms on the product side. You can't have more carbon atoms on one side versus another. You're going to violate the law of conservation of matter. Now, what we do is we indicate the physical states of our reactants and products by using these subscripts. So G is for gas, S is for solid, L is for liquid, and AQ is for aqueous. And aqueous means that it was a solution with water in it, or it's in water. So aqueous, the solvent, is water that is used. So for example, we have a reaction of methane with oxygen gas to form carbon dioxide and water vapor. So to form means we're going from reactants to products. So we have oxygen gas, we have methane, they react, they form carbon dioxide and water vapor. So if we wanted to write this chemical reaction, it would look like this. Now remember that oxygen gas is diatomic, so make sure you take note of what's called Brinkel-Hoff, which is an acronym for all the diatomic molecules on the periodic table. Next we have a reaction involving solid potassium with water to form, again that word to form, hydrogen gas and potassium hydroxide dissolved in water. So to form indicates that water and potassium react to form our products, hydrogen gas and potassium hydroxide. One thing you have to remember is that hydrogen gas is diatomic. It's going to be H2. So we have potassium plus water yields H2 plus potassium hydroxide. Now, since it's dissolved in water, we use the subscript AQ. So this is how you write chemical equations describing a chemical reaction. Now we're going to look at balancing chemical equations. So when we're balancing chemical equations, what you have to remember is that atoms are conserved. There's no net loss of a particular type of atom. Secondly, never change the formulas of the compounds when balancing equations. So you can't, for example, have H2O and then just say you're going to balance the oxygen by putting a 2 there. That is incorrect. So you can't change the subscripts in a chemical formula. You can only change the coefficients, which are the numbers that come in front of the reactants and products. Please note that when there's nothing in front of a reactant or product, that counts as 1. Just like if you had an equation with x plus 7, for example, equals 3, there's understood that there's a coefficient of 1 in front of the x. So if there's nothing in front of the reactant or product, it's assumed a coefficient of 1. So now when balancing equations, there's really not a set list of rules, just a few guidelines to help, guide you to balance the equations. Now I can give you some tips along the way, but practice is what makes perfect. So for example, here we have H2 gas plus O2 gas gives us H2O. So the first thing you want to do is determine the number of each element on both sides of the equation. Well, we have 2 hydrogen on the reactant side, 2 hydrogen on the product side. On the reactant side, we have 2 oxygen and 1 oxygen. So just by determining the total of each atom, we know that oxygen is not balanced. So to balance the oxygen, we put a 2 here. Now the oxygen are balanced, but now you'll see that on the product side, we have 4 hydrogen. On the reactant side, we have 2 hydrogen. And so we have to put a 2 here on the reactant side to give us 4 hydrogen. And this is the balanced chemical equation. Now, one thing to remember is that the lowest common multiple of coefficients has to be 1. If it's not 1, then you need to factor out what's common and make it 1. So for example, if we were to put 4, 2, 4, this is balanced, but the lowest common multiple is not 1, so you'd factor out the 2, we would get 2, 1, 2. So always make sure that when balancing equations, the lowest common multiple between the coefficients is always 1. If it's not, then you're going to lead into issues when balancing. So that's that one. Now we go to the second equation. We have C2H5OH plus O2 gives us CO2 and H2O. So here you see we have multiple atoms. Some occur in every reactant and product, some occur in one. And generally, this is a general guideline. If you have hydrogen, oxygen, and other atoms, it's always good to balance the other atoms first, and then the hydrogen and oxygen. So I'm going to balance the carbon first. So this carbon has 2. I'm going to put a 2 in front of the CO2. So now my carbon are balanced. Next, we have to decide between hydrogen and oxygen. So another guideline to use is generally you want to balance an element that only occurs in one reactant and product versus one that occurs in multiple reactants and products. So on that note, I'm going to balance the hydrogen next. So here we have 6 hydrogen. To turn this into 6, we got to use a 3. So now the hydrogen are balanced. Now we need to balance the oxygen. So we have 5 oxygen on the product side, 3 oxygen on the reactant side. Well, we don't want to put anything in front of ethanol, C2H5OH, so we want to put something in front of this O2 to give us 5 hydrogens. So we put a 2 here. You see now we have 5 oxygen on both sides. And so this is the balanced chemical equation for this reaction. We'll go through a few more examples. Practice makes perfect. So here we have NO plus H2 gives us N2 plus H2O. So we notice here that the hydrogen is balanced, 2 and 2. Oxygen is balanced, 1 and 1. But we notice the nitrogen is not balanced. So we have 2 nitrogen on the product side, 1 nitrogen on the reactant side. So we got to put a 2 here. So now that we put 2 nitrogen, or 2 in front of the NO, we have 2 nitrogen and 2 nitrogen. But now you see we have also 2 oxygen on the reactant side. We got to have 2 oxygen on the product side. So then we put a 2 in front of the H2O. Now we have 2 oxygen and 2 oxygen. But you'll notice the hydrogen has changed on the product side. Now we have 4 hydrogen on the product side, 2 hydrogen on the reactant side. We're going to need a coefficient of 2 on the reactant side. So now this is the balanced chemical equation. Next we have Fe plus O2 gives us Fe2O3. So here we notice there's iron is not balanced because there's 1 iron to 2 iron, and oxygen is not balanced, it's 2 to 3. So here, since iron is only 1 on the reactant side, anything we put in front of Fe2O3 we can easily balance with iron. So oxygen is 2 and 3, so that's an even-odd combination, so we got to make a common multiple between 2 and 3, which is 6. So we're going to put a 2 here, and that means we have 6 oxygen. We can put a 3 here, so now we have 6 oxygen. So we have 4 iron. We can easily put 4 iron on this side. So now we have a balanced chemical equation. Moving to the next one, we have NO gives us N2O plus NO2. So you see that we have a total of 3 nitrogen on the product side, 1 nitrogen on the reactant side. We have a total of 3 oxygen on the product side, 1 oxygen on the reactant side. So we just need to put a 3 in front of NO. And now the equation is balanced. Lastly, we have this combustion reaction involving ammonia. NH3 plus O2 gives us NO and H2O. So since we have a non-hydrogen oxygen element, we should balance that one first. So we have 1 nitrogen and 1 nitrogen. So that's balanced. Next, we need to balance the hydrogen. And we have 3 hydrogen and 2 hydrogen. So in order for 3 and 2 to be a common multiple, again, it's an even-odd combination, we need 6 hydrogen. So to make this 6 hydrogen, we're going to put a 2 here. So now we have 6 hydrogen, and we're going to put a 3 here. Now we have 6 hydrogen. But notice that the nitrogen changed. So now we have 2 nitrogen and 1 nitrogen. So we put a 2 here. So notice now what we've done is we have a total of 5 oxygens on the product side, 2 oxygen on the reactant side. So there's no whole number we can multiply by 2 to get 5. So what I'm going to do is I'm going to double all my current coefficients to make this 4, make this 4, and make this 6. Again, the reason I'm doing that is because there's nothing I can multiply by 2 as a whole number and get 5. So when we do it this way, you see we have a total of 10 oxygen on the product side. So now we can put a 5 here and make 10 oxygen on the reactant side. And notice that the common multiple between the coefficients is still 1. So now we have a balanced chemical equation. So this is just kind of an overview of how you go about balancing chemical equations. Now we're going to look at reaction types. So there are two broad groups of reactions. These are called double displacement reactions, or referred to as metathesis. It's the same thing, double displacement or metathesis reactions. In these types of reactions, cations and anions switch. So if we have the AB and DC reactants, the cations of each of those are going to switch to form two new products. And there are two main groups of double displacement reactions: precipitation reactions and acid-base reactions. Now that's one separate category of reactions. So remember, these don't cross. These are independent reactions. If you're double displacement, you cannot be the next one, which is redox. And so redox reactions involves the transfer of electrons. And if you're taking the lecture, you've taken the lecture, you know how to determine or identify if electrons are being transferred in a reaction. So that you'll learn in the lecture. What I'm going to talk to you about is the different types of redox reactions. So the first type is single replacement, and we're going to talk about in depth in all these in just a moment. So single replacement is a type of redox reaction. Combustion is a type of redox reaction. Synthesis, or sometimes referred to as combination, is a type of redox reaction. But note the asterisk. The asterisk means that certain types of synthesis or combination reactions are not redox. And we'll talk about those in just a moment. Decomposition, again an asterisk, because certain types of decomposition reactions are not redox. So we're going to go through each one and give you an overview of the characteristics of each type of reaction. But again, if you're double displacement / metathesis, you cannot be redox. There's no crossover between the two. So first we want to look at precipitation reactions. Let me clear this up. So for precipitation reactions, you're going to need two soluble ionic compounds to react to form an insoluble, at least one insoluble precipitate. Again, the reactants have to be soluble compounds, so of course we're going to be looking at solubility rules. And they have to form at least one insoluble precipitate. Again, this is a double displacement / metathesis reaction. So for example, we take silver nitrate, which is a solution, sodium chloride, which is a solution. We mix these, we get silver chloride, which is our precipitate, and sodium nitrate, which is still in solution. Now the reason we know that silver chloride is a precipitate is based on what we call solubility rules. So by knowing the solubility rules, we know that silver chloride is an insoluble solid. And so what happens is when you mix sodium chloride and silver nitrate solution, you form a white precipitate, which is silver chloride. And again, the way we know that it's silver chloride is based on the solubility rules. So what are the solubility rules? So when you're answering questions on the lab lecture quiz, make sure you adhere to these solubility rules posted here. Don't look at your textbook, don't look at other sources, because for the slightly soluble cations, there are some differences in different solubility rules. So when you're looking at the lab lecture quiz questions or any solubility dealing with the post-lab assignment, make sure you refer to this chart here. Now to give you a few key pointers, for example, all nitrates are soluble. So any nitrate salt that you see is going to be aqueous. All acetates are soluble except for the ones with silver plus. So silver acetate would be an insoluble salt. Now the halides, which is your chloride, bromides, and iodides, there are 4 cations that are insoluble. All other cations are soluble. Again, these are referred to as halides because they contain group 17 anions. Oh snap, let me undo that. Yep. So for halides, all of them are soluble except silver, lead 2+, mercury 1, and copper 1. So if it's one of these 4 cations, it's going to be an insoluble halide. Now for sulfates, all sulfates are soluble except these 5 cations: barium, strontium, lead 2, silver, and calcium. All other sulfates are soluble. Another one I want to touch base on is hydroxides. And all hydroxides are insoluble because remember, this is the insoluble column. So everything on this side generally are insoluble. Everything in the middle column are soluble columns. So these are the cations that are soluble. And so you see for hydroxides, ammonium cations in group 1 and barium, strontium in group 2 are soluble hydroxides. So this is how you interpret this solubility table. Now, sodium group 1 cations and ammonium cations are always soluble regardless of the anion. So anytime you see a group 1 salt or an ammonium salt, you know automatically it's a soluble salt. So make sure you look over these solubility rules because they're important to determine the precipitate in precipitation reactions. So to give you some examples, here we have different precipitation reactions. So if we're doing double displacement, the lead comes here. The potassium bonds to the chlorate, and then you would look up your solubility rules, and you will know that lead 2 carbonate is insoluble, potassium chlorate is soluble. Again, potassium chlorate is a group 1 salt, it's soluble. Next, we're going to make, we have 2 aqueous solutions. The nickel reacts with the hydroxide, the potassium reacts with the sulfate. We get 2 new products. And based on the solubility rules, we know that nickel 2 hydroxide is insoluble and potassium sulfate is a group 1 salt, it's soluble. Next we have copper sulfate. So the copper reacts with the chloride, the zinc reacts with the sulfate. So in this case, we get no reaction because both products are soluble. Zinc sulfate and copper 2 chloride are soluble salts, so there's no reaction that occurs. Then we have barium reacts with sulfate, iron reacts with hydroxide. And so in this example, we get 2 precipitates. We get iron 2 hydroxide is insoluble and barium sulfate is insoluble. Most of the time you'll get 1 precipitate. A few times you may encounter 2 precipitates, or you may encounter no precipitates. So again, the way I know that lead 2 carbonate, nickel 2 hydroxide, iron 2 hydroxide, and barium sulfate are solids is based on the solubility rules. The other type of double displacement reactions, so again, these are double displacement metathesis. is acid-base reactions. And the unique thing about acid-base reactions is that they always form a salt and water. And generally, if we're looking at strong acid and strong base reactions, the salt is going to be the cation of the base and the anion of the acid. So if we have HCl plus NaOH, the Na and Cl form the salts, and then we get H2O. So you may be asking, what are the strong acids? So right here are the 6 common strong acids. So it's very good if you remember these. It's very important later on down the road. And our strong bases are going to be the group 1 and heavier group 2 hydroxides, strontium and barium, listed here. So anytime you have an acid-base reaction, you're always going to form salt and water. So here we have a strong acid, perchloric acid, reacts with potassium hydroxide. So we do double displacement. The hydrogen, the H plus, reacts with the hydroxide. The potassium cation reacts with perchlorate. We get a salt and water. And this, my friends, should not be solid. It should be aqueous. That's a mistake. Aqueous. All right. Next, we look at HNO3 and strontium hydroxide. So again, the H plus reacts with the hydroxide. Strontium reacts with the nitrate. We get strontium nitrate, and again, it's not a solid, it's aqueous. And H2O. A lot of cutting and pasting, I guess. Now, if you react with strong acid with a weak base, you still get a salt, but you get other things as well. So here we're reacting nitric acid with sodium carbonate. So again, the H plus reacts with the carbonate. The sodium ion reacts with nitrate. And since this is a carbonate, we produce CO2 as a byproduct as well. So we still get our salt in NaNO3. We get water, and we also get CO2 because we're reacting an acid with a carbonate. Lastly, we have HF, which is a weak acid. So the H is going to react with the hydroxide of the strong base, and the sodium is going to react with the fluoride. And so here we get a salt and water as well. So again, acid-base reactions are a type of double displacement metathesis reactions. Now we're going to be shifting gears and talking about redox reactions. And again, redox reactions involve the transfer of electrons. Now, the first one is combustion. And combustion reaction is a fuel, and this doesn't have to be a carbon-based fuel. This can be any type of fuel. Reacts with oxygen to produce oxides of the fuel. Now, commonly we use hydrocarbons, which contain carbon and hydrogen. So this is the fuel. So since our fuel is made up of carbon and hydrogen, we're going to get oxides of carbon and hydrogen, namely CO2 and water. And as I said earlier, this produces a lot of energy. A lot of heat is produced. And it produces gas as well. So we look at some other examples. So we take propane plus oxygen. Since we're using propane contains carbon and hydrogen, we're going to get oxides of carbon and hydrogen. C6H14, again, reacts with oxygen. So we have some fuel. Again, this is the fuel. Reacts with oxygen gas, and we get oxides of the fuel. And if you use a hydrocarbon, the oxides are carbon and hydrogen. Now, it doesn't just have to be a hydrocarbon. You can use a nitrogen-based compound, for example, or sulfur. Here we're using nitrogen. Again, this is our fuel, reacts with oxygen. Now we get oxides of nitrogen and hydrogen. So the things you're looking for a combustion reaction, you're looking for a fuel as a reactant, oxygen as a reactant, and you form oxides of the fuel as products, and a lot of energy is released. Synthesis reaction, here the characteristics are you have two or more reactants, gives you only one product. And so that's the key, is there's only one product in a synthesis reaction. Now when your reactants are elements, it's always going to be redox. When your reactants are not elements, it may or may not be redox. So here we have the synthesis of glucose. So we have elements on the reactant side and a compound on the product side. Here redox has occurred. Because anytime you have elements on one side and it's in a compound on the other side, there has been a transfer of electrons. Next we have the synthesis of calcium oxide. So we take calcium plus oxygen, gives us calcium oxide. Again, we have our reactants are elements. We form one product, it's synthesis, and since it's elements on the reactant side, redox has occurred. One more example. So here we take SO2 plus water, we produce sulfurous acid. And in this case, we have compounds, gives us a synthesized into one product. And here, redox has not occurred. So this is synthesis, but redox has not occurred because we start with compounds and we end up with a compound. So again, synthesis, if your reactants are elements, you form a compound, redox has occurred as well. If they're compounds and form a compound, redox may or may not have occurred. And in this example, it did not occur. So decomposition is the opposite of synthesis. So here the key characteristic is one reactant forms two or more products. And if your products are elements, then redox has definitely occurred. If your products are not elements, redox may or may not have occurred. So we look at the decomposition of pentane. It decomposes into carbon and hydrogen. Here, since we produce elements, redox has occurred. We look at the next example. We have the decomposition of silver nitrate into silver, oxygen, and nitrogen. Since we produced elements, redox has occurred. So we went from a compound to elements, definitely redox has occurred. Next, we take calcium carbonate. It decomposes into calcium oxide and CO2. Now this is decomposition, but this is not, redox has not occurred. I don't know what's. So again, if your compound decomposes into elements, redox has occurred. If it has not, then if it decomposes into compounds, it has not occurred. And let me, made a typo here, it needs an extra R, occurred. 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 My bad on that. Now the last type of redox reaction is single replacement. So here, single replacement, the characteristics is an element replaces another element in a compound. So you're always going to have an element on the reactant side and an element on the product side. So here, redox always occurs. So for example, we take magnesium, reacts with water, the magnesium displaces the hydrogen, and we form magnesium hydroxide and H2 gas. Again, like I showed you earlier, when you have a metal and an acid, typically this is going to produce a gas, and it's going to be usually hydrogen gas. Now, the way we know that a metal will replace another metal is based on the activity series. So this tells you which elements are more active than others. So for example, if we take aluminum and put it in a solution of copper chloride, aluminum displaces the copper, and we form aluminum chloride and copper solid. Again, aluminum is more active, so it wants to be with a compound, and copper is less active, it wants to be an element. Next, we take nickel and put it in hydrochloric acid. Nickel displaces the hydrogen, and the hydrogen leaves. We form nickel 2 chloride and H2. And this is because nickel is more active than hydrogen. And then one more example, and even halogens can displace other halogens. And so the reactiveness of halogens is fluorine is the most active, then chlorine, then bromine, then iodine. So halogens have their own activity series. So halogens will displace other halogens. So here fluorine displaces the iodine. Iodine leaves because fluorine is more active than iodine, so we form sodium fluoride and I2. So all of these are redox reactions as well, because you always form an element, and we always had an element on the reactant side. So what is this activity series? Well, this is a chart that kind of shows you, oh, this one more. So now if you try to react nickel with potassium chloride, nickel will not displace potassium chloride or potassium because potassium is more active than nickel, and so potassium is happy. So there's no reaction when nickel reacts with potassium chloride because potassium is more active than nickel. So this activity series, the more active metal will replace the less active metal. So if your element is more active than the cation in the compound, then the reaction will occur. So things like lithium, potassium, calcium, sodium are very active. Things like gold, platinum, and silver are less active. Now, you do not have to memorize this table. You'll be provided for you on questions, but you do need to know how to utilize the table. So here we have three solutions. We have copper plus HCl, aluminum plus HCl, and zinc plus HCl. And which one of these will cause a reaction, which ones will not? And so if we look at the copper and HCl, no reaction occurs because copper is less active than hydrogen. It's not going to displace the hydrogen from hydrochloric acid, so no reaction will occur. We look at aluminum. Aluminum is more active than hydrogen, so a reaction will occur because aluminum will displace the hydrogen, so that aluminum becomes a cation and hydrogen becomes H2 gas. Next, we have zinc and HCl. So since zinc is more active than hydrogen, zinc will react with HCl. Now, since aluminum is higher than zinc, aluminum will react more vigorously with hydrogen than zinc will. So the further up or the greater the difference between the elements, the more vigorous the reaction. So aluminum will react a lot more vigorously than it would with zinc because aluminum is more active than zinc. Both of them will react with HCl, but aluminum will react more vigorously because it's further from hydrogen. So now if we take zinc and HCl, again, zinc is more active than hydrogen, so zinc will displace the hydrogen, and we produce hydrogen gas, which is denoted by the bubbling in the test tube. We look at magnesium and HCl. Magnesium is more active than hydrogen, so magnesium is going to displace the hydrogen and form magnesium chloride and H2 gas. And since magnesium is further from hydrogen, magnesium would react more vigorously than zinc would with HCl. Then if we try to react silver with HCl, since silver is less active than hydrogen, it will not displace the hydrogen, so no reaction would occur. So again, you don't have to memorize the activity series, you just have to be able to utilize it to determine what reactions will or will not occur. So what's your to-do list? Make sure you read over the lab lecture notes, watch the lab lecture video. I give you more information on the video that's on the notes because I explain everything. Read over the background information for the chemical reaction types lab. Do the balancing equations practice assignment first, and then do the lab lecture quiz for this lab, and then complete the virtual lab on the Hayden McNeil site. And once you're done on that, then start on the post-lab assignment for this experiment. So I hope today's lecture was informative, and if you learned something new or liked the lecture, make sure it's always nice to hit the like button at the bottom of the screen. And so on that note, until next time, Dr. Armand signing off.